In this fourth presentation, on multiphase displacement, we begin the analysis of the fractional flow curve. The first objective is to analyze the correction factors used to adapt the fractional flow curve to systems that include capillary and gravitational forces. As we will see, the correction factors are not applied to the Rel Perm curves, but directly to the fractional flow curves. This adaptation is made to be able to apply the excellent properties of the fractional flow curve to scenarios much more complex than those for which these curves were originally defined. The second objective, necessary to establish the validity of the aforementioned corrections, is to clarify and deepen the concept of relative permeability. During this analysis, we will discuss the uniqueness, or not, of the Rel Perm curves for a given set of porous medium and fluids. The previous presentations, where we detailed the complexity of real scenarios, can be summarized as follows. Using average values to simplify complex scenarios leads, for example, to describe the complexity of this fractal picture. Using a single, average color. We do the same, to some extent, with real multiphase displacements, when we average the diversity of saturations and flow conditions through Rel Perm curves, or the associated fractional flow curves, trying to describe the movement of several phases in the same porous medium using a point saturation value as reference. This saturation allows us to model what happens at the production end, but does not describe the heterogeneity of saturations and flows along the sample, for each of the phases, during real displacements. We also considered this phrase, which is an excellent reminder of the importance given to the Rel Perm curves during the modeling step in reservoir engineering. In this presentation we will look in detail that, despite the fact that the original use of the fractional flow curve was introduced simultaneously with the frontal advance theory, this curve exceeds the theory itself. We will appreciate that, trying to eliminate the initial restrictions of the frontal advance theory, corrections are incorporated directly in the fractional flow curve to include the effects of capillary and gravitational forces on multiphase displacements. This procedure is done with the intention of describing scenarios much more complex than those originally defined by both Buckley and Leverett and Welch. At this point, it is good to remember that natural systems cannot always be described through simple models. Mandelbrot, in the introduction to fractal geometry, is very accurate when he says that what we do regularly in science, and we could also add in technology, is to use increasingly realistic models. We start from simple, continuous, homogeneous representations and then we add corrections in such a way that we get closer and closer to the correct solution. But there are domains in which reality, as Mandelbrot says, is so irregular that the continuous and perfectly homogeneous model fails and cannot even serve as a first approximation. Well, we will see that in the 1942 publication the situation is very close to what Mandelbrot referenced. In the original work of Buckley and Leverett, they describe a first scenario, defining a homogeneous linear system, controlled by viscous forces, and then add corrective terms trying to make the front advance theory more realistic. The fractional flow curve, as presented by Buckley and Leverett, in 1942, for linear flow, includes a very simple analysis derived from Darcy's law, corrected for multiphase flow. So that, for a given water saturation the corrective terms of the equation adopt the form of a Rel Perm curve, that, in the absence of capillary and gravitational forces, that is, where we can ensure that the pressure difference to which the water phase is subjected is identical to that of the oil phase, allows the calculation of the fractional flow curve through a very simple expression that links not only that fractional flow curve with the Rel Perm curves but with the viscosity ratio of the fluids. If we select a Rel Perm curve and take into account the viscosity ratio between water and oil, we can calculate, as we have seen, the fractional flow curve. In this case, a viscosity ratio with a value of 1 was used, which means that oil and water have the same viscosity. If the oil phase viscosity is 10 times that of water, the fractional flow curve changes, moving towards lower water saturations. And if the oil viscosity becomes 100 times greater than that of water, the fractional flow curve, always for the same Rel Perm curve, shifts even more towards lower water saturations. This shift indicates that, as the oil viscosity increases, water becomes more inefficient to displace oil. As a result, for the same water saturation, the more viscous the oil is, the more water is flowing. If we choose one of the fractional flow curves that we saw in the previous slide, we can study, through graphic analysis, the equations that go together with the frontal advance theory. In this way, if we draw a tangent to the fractional flow curve, a tangent that starts at the point of irreducible water saturation, the value of water saturation at the contact point defines what we know as the water saturation at the breakthrough, that is, at the arrival of the waterfront to the production end. And if we continue the tangent line, the point where it intersects the upper axis defines the average water saturation of the sample at the same time. We can appreciate that, when the saturation at the production end is just above 50%, the second point shows that the average water saturation of the system is close to 60%. These characteristics of the tangent line remain valid throughout the entire oil production process. Any tangent drawn later indicates, at the point of tang in C, the saturation of the production end, while the intersection point with the upper axis indicates the average water saturation of the system. Both values become identical at the end of the displacement because, under these conditions, the entire system is in residual oil saturation. An important detail is that, when the waterfront reaches the production end, a saturation jump occurs, going from the irreducible water saturation to the waterfront saturation, without going through the intermediate saturations. In this way, the section of the curve that at this moment is dotted is only a mathematical calculation without physical meaning, since these point saturations do not exist at the production end, or in any specific location within the porous medium. As we have just seen, the fractional flow curve has very simple properties and graphically describes the equations of the frontal advance theory. As a consequence, it is very attractive to use just the fractional flow curve to characterize multiphase displacements. However, when we consider, even a linear system like the one originally analyzed by Buckley-Leverett and later by Welch, and we want to include the capillary and gravitational phenomena, the calculations are no longer that simple. Since the pressure differences for water and oil are not the same, the different fluids densities and the capillary pressures generate different pressure gradients for each phase. Then, it is mandatory to include corrective terms. When doing the math, the corrective terms adopt this form, where the difference in fluids density and the dip angle of the structure are taken into account to calculate the impact of gravitational forces. The capillary pressure change, as a function of water saturation, is also taken into account. In linear systems, this is equivalent to linking the change in capillary pressure to distance. However, these corrections do not take into account that, if we include the capillary and gravitational forces, the Rel Perm curves also change. That is, these corrections take into account the different pressure gradients for water and oil, but they assume that the Rel Perm curves are independent of the equilibrium between the pushing forces. To understand why changing the balance of forces modifies the Rel Perm curves, it is necessary to deepen into the concept of relative permeability. Let us study a very simplified porous medium. In fact, a bunch of cylindrical capillaries. Once the area of the block that we are going to characterize has been defined, if we begin with a certain number of capillaries, the porosity grows with the square of the radius of the capillaries, since their area grows with the radius squared. Instead, the flow rate obtained, after applying a pressure difference between the ends of the block, grows with the fourth power of the radius, as described by Poiseuille's law. Here we can see a prismatic block with a square base, whose side we identify with the value x. In principle, we will include a single cylindrical tube that runs from end to end. If we consider a plane that cuts this block, this plane defines a face within the system, which, schematically, allows us to do the same type of analysis than the frontal advance theory. This is the face defined by the plane in the previous slide. We arbitrarily set the value 1 for the radius of the capillary, and we can choose the parameters so that the permeability corresponds to 0.1 millidarcy and the porosity has the value of 0.1%. These values are obtained when the prism side and the radius of the capillary are those indicated on the slide. If we now also consider a single capillary but with a radius that doubles the previous value, as the porosity grows with the square of the radius, we go from 0.1% to 0.4% porosity for the same block. At the same time, as the flow rate increases with the fourth power of the radius, the calculated permeability for this new block is 16 times greater than that of the block with a single capillary of unitary radius. Consequently, the new block has 1.6 millidarcies permeability. If, finally, we consider a single capillary of radius 3. In this case the porosity represented by that single tube is 0.9% of the total volume of the system and the permeability becomes 8.1 millidarcies. Now, let's consider a more complex block, including capillaries of diameter 1, diameter 2, and diameter 3. With the intention of including families of capillaries that we could identify as small pores, medium pores, and large pores. In this diagram we are seeing 100 capillaries of radius 1, 20 capillaries of radius 2, and 10 capillaries of radius 3. As the tubes are independent from each other, we can additively calculate both the porosity and the permeability of the system where each capillary may be seen as a pore. As we have 100 pores of radius 1 and each pore contributes with a porosity of 0.1%, these 100 pores generate a porosity of 10%. The same happens with permeability, as there is no interference, each capillary, or pore, transports its corresponding flow regardless of the presence, or not, of other capillaries. In this way, the flow associated with 100 identical pores will be 100 times greater than the value corresponding to a single pore. As a consequence, this family of small diameter pores provide a permeability of 10 millidarcies. The same calculations made for the medium and large pore families yield porosity and permeability values that, added together, produce a porous medium with 27% porosity and 123 millidarcies of flow capacity. If we now consider that the block is flooded 100% with water, the water permeability is 123 millidarcies, matching the absolute permeability of the block. In this other case, the block is flooded 100% with oil, there is no water in any of the capillaries. Now the permeability to oil is equal to the absolute permeability of the system and the effective permeability to water takes the value 0, since, no matter how much pressure difference is applied, the water flow capacity remains null. If we now begin to flood the pores with water, they will fill following a sequence dictated by the capillary forces. The smaller diameter pores will flood first. If we analyze the situation when only 10 of these small pores have been invaded by water, we can calculate that the water saturation at this time is only 3.7% of the pore volume of the system, while the oil saturation is the complementary value, 96.3% of the pore volume. At this time the water flow capacity is 10 times that of an individual pore of the smaller diameter, totaling 1 millidarcy. While the effective permeability to oil is the complementary one to reach 123 millidarcies. This allows us to obtain the Rel Perm value to water of 0.0081. And Rel Perm to oil, which retains above 99% of the absolute permeability of the block. If the smaller diameter pores continue to be filled with water, there comes a time when they are all completely flooded. At that time, the water saturation is 37%. and the oil saturation is 63%. Water permeability is 100 times greater than that one individual pore. This is 10 millidarcies. And the remaining 113 millidarcies are left to conduct oil. At that time, the Rel Perm to water is 0.081. The effective permeability to oil is still greater than 90% of the absolute permeability of the system, despite the fact that there is already 37% of water occupying the Pearl network. This happens because the water is occupying the pores with the smallest diameter of the system, which are the ones that provide the least flow capacity. If we continue with filling the pores, at the moment this image shows, the pores of intermediate diameter are already flooded. When doing the math, the water saturation is almost 67%. Oil saturation is complementary. Water permeability has already grown to 42 millidarcies. And that of oil was reduced to 81 millidarcies. In this way, the corresponding relative permeabilities adopt these values. At 67% water saturation, the relative ability to conduct oil is still greater than that of water because oil completely occupies the largest channels in the Pearl network. When the analysis is complete, we can visualize the Rel Perm curves for this block. The irreducible water saturation is 0 because we assume that, in each pore, one phase displaces the other phase with 100% efficiency. Therefore, each pore goes instantly from 100% oil to 100% water, as displacement occurs. As we have already seen, a water-wet medium is assumed. And the mechanism chosen for the displacement is dominated by capillary forces. That is why the replacement of oil with water begins with the smaller diameter pores, where the capillary forces, being more intense, favor the entry of the wetting phase. Once we have established how to calculate the Rel Perm curves, an important question arises: can we have other displacement curves associated with this same porous medium? As we will see, the answer is positive. If, instead of having a water-wet porous medium, we had an oil-wet porous medium, the lowest resistance to the entry of the non-wetting phase, water, is presented by the larger diameter pores. As a consequence, the displacement of oil by water begins in the largest pores. And, subsequently, increasing the displacement force continues to displace the oil from the intermediate diameter pores. And finally the oil from the pores of smaller diameter is also displaced. In this case the curve obtained is complementary and totally different from the curve we got for the case of a water-wet porous medium. It is important to mention that a similar result would be obtained in the case of a displacement under the domain of viscous forces, with a very high pressure difference. In this case, although the system may or may not be water-wet, a very high pressure difference, dynamic viscous displacement occurs first in the pores with the largest diameter. Then, this set of curves represents both the behavior of an oil-wet system and that of a very high pressure difference, very high flow rate displacement system. If instead of analyzing a displacement dominated by viscous or capillary forces, we were to analyze a displacement dominated by gravitational forces, the displacement scenario would change again. We can imagine that this is a block of parallel layers, which is being flooded by water. Assuming that water has higher density than oil, water will first invade the lower levels in the structure, regardless of whether they are those with a smaller, intermediate, or larger diameter. Later, when the water level rises, it will keep it invading the pores that it finds, one more time, regardless of whether they are those with a smaller, intermediate, or larger diameter. The curves obtained at the end of this displacement are also different from those we have already observed, because in this case the filling does not follow the sequence of diameters but rather a spatial location sequence. Additionally, if the spatial distribution were not in layers or sheets as we saw in the previous case, but random, the same gravitational filling would have led to the generation of different-looking Rel Perm curves. In fact, possibly for many of those who are seeing this presentation, This is the typical way to represent Rel Perm curves under the domain of gravitational forces. In this case, it is easy to explain this characteristic, since, as the water level rises, the increase in water saturation matches the simultaneous flooding of small, medium, and large diameter pores. Under these conditions, higher water saturation implies a linear increase in water conduction capacity, and that situation generates the Rel Perm curves we are seeing. Consequently, when we go back in time and review the assumptions made by Buckley and Leverett in 1942, it is clearly understood why these authors decided to eliminate capillary and gravitational forces during the study of multiphase displacement in a linear and homogeneous system. Had they been taken into account, the fractional flow curve would have not been independent of the balance of forces for the same saturation of the displacement phase, and this was a necessary assumption to derive a single displacement curve. As summary and main comments of this presentation, we can say that the Rel Perm curves, which are the ones that allow the generation of the fractional flow curve, considering the viscosity of the fluids, are different for each balance of forces. That is, there is no single set of Rel Perm curve when all forces involved in fluid displacement are accounted for. If we obtain Rel Perm curves dominated by viscous forces, which is what is done at the laboratory level, and we want to adapt the fractional flow curve to scenarios that include capillary and gravitational forces, we also have to change the Rel Perm curves. We are going to see this situation, in a dramatic way, during the next presentation. To some extent, the same erroneous oversimplification is made in numerical simulation when the potential field is calculated taking into account all the intervening forces, and, then, the transport of fluids is modeled using a single set of Rel Perm curves. Finally, the properties of the fractional flow curve, which we looked at the beginning of this presentation, are only valid for the frontal advance theory, without participation of capillary and gravitational forces. Then, these properties cannot be generalized to real scenarios, three-dimensional, heterogeneous, and exposed to a variable balance of forces. What we are going to see, in the next presentation, is an application of the fractional flow curves through an example where it is clearly demonstrated that, if the properties of the fractional flow curve are transferred to real situations, we get results that are incompatible with physical reality.